everyone. Today we are going to take a look at this idea of rates of change, and this is what calculus is all about. So this lesson is a big one. I don't think there's much that's real difficult mathematically in this lesson, but it's really laying the foundation for what the entire rest of the class is going to be about. So I'm going to start with some stuff that you should already be familiar with. Maybe you don't know the vocabulary necessarily, but you've done this before. So starting out with average rate of change, and if you need to pause to get that definition down, feel free. It's the average change in the dependent variable. I'm going to break this down a little bit. Dependent variable, that's talking about your y values, okay? And to find the change in y values, we would subtract them, okay? That tells us how much the y values have changed per, so that's implying division, right? Something per something. Per unit of the independent variable. So what this is really talking about is like for every one of whatever the independent variable is, how is the y changing, okay? Or in other words, we're going to take our y values and subtract them and then divide that by the change in the x values. This should look familiar to you. This is what we refer to as AROC, okay, average rate of change. Some of you are looking at that and saying, well, that's just slope. You're not wrong. Slope is a very specific type of average rate of change that works specifically with linear equations. We can do average rate of change on anything. So for example, on this graph over here, I could find the average rate of change between, let's say, this point right here and this point over here, okay? And if I were to calculate that average rate of change, what I would find is the slope of this line, okay? So slope is specifically talking about a straight line, but that is the slope of that is the average rate of change, okay? That line, by the way, that I just drew, that is called a secant line. So a secant line is a line that intersects a graph in 2 points, and these are useful for finding average rate of change. So essentially the average rate of change is the slope of the secant line. Okay? All of that is stuff you've done before. This is all stuff you've done in algebra. We're going to do an example right now of one of these, but it should look entirely familiar to you. Maybe you didn't use this notation before. This interval from 1 to 3, remember these are your x values. So what we need are the coordinates that go with those x values. So we need to think of like, you know, it's 1 comma something and 3 comma something. Okay, and I'm going to plug those into this function. So 1 squared is 1 and 1 minus 1 is 0. So this y coordinate would be 0. 3 squared is 9, and 9 minus 3 gives me 6. So these are my two coordinates. And again, these came from using my y value, right? I found f of 1 and f of 3. Okay, so now to calculate my average rate of change, I'm going to do y2 minus y1 over x2 minus x1. Actually, doesn't matter which order you go in here as long as you do it consistently with the top and the bottom. Okay, so let's see, that's 6 over 2, so I would say that my average rate of change here is 3. So if I looked at the line that connected these 2 points, that line would have a slope of 3, and on average, that's how fast this line is changing. Now, average rate of change is great. It can be helpful, but it can be a little misleading. So let me give you an example here. If I'm looking at this function again, which, by the way, this is not this function, and I were to look at this average rate of change, it would be negative because the slope is negative here. And that would make me think that this function is decreasing between here and here. And I mean, it did decrease, right? It got smaller if I go from this point to this point. But that's not all it did. It actually increased for a while and then started decreasing again and then increased some more. So average rate of change is great for like the big picture, but it doesn't give you a whole lot of information about what is actually happening with the function. Okay, sorry about that. So this is where calculus starts, is right here, okay? Calculus is not concerned so much with average rate of change. Calculus is concerned with what's called the instantaneous rate of change. We don't want to know what's happening on average. We want to know how are things changing right at one particular point. Okay? So the specific rate of change at a single point on a function. So I want to be able to look at this point right here and say, how fast are things changing at that particular moment? And for that, I'm going to use what's called a tangent line. So a tangent line touches the graph in only one point, like this. Now, you'll notice it does come down here and cross the function again. That happens sometimes with tangent lines. We're not going to use that point or anything. We are just going to focus on this one spot right here. That's called a point of tangency. So the instantaneous rate of change is found by drawing a tangent line, which has an intersection of exactly one point, and the slope of that tangent line gives us the instantaneous rate of change. Okay, so again, these two things are connected because the instantaneous rate of change is the slope of that tangent line. Now the problem is, we only have one point to work with here. Remember, we can't really use this point because we don't know exactly where these two things are going to cross. A lot of functions, I mean, if this is a parabola, we wouldn't even have a second point over here. So I only have one point to work with here. I can't use my slope formula, right? I can't use this if I only have one point to work with. And that is what calculus is being able to find the slope of a tangent line to a function. We are going to talk about tangent lines and instantaneous rates of change probably every day from here to the end of the class. And that has a special name. That slope of the tangent line is called the derivative. Derivative is the slope of the tangent line at a single point. I don't think there will be a single day in this class from here to the end of the year that we don't talk about derivatives in one way or another, because that is what calculus is concerned with. Anything in life where you're talking about how quickly things are changing or by how much are they changing, that's using calculus. Okay. Let me throw a couple of symbols your way, even though I don't think you really need them quite yet in this lesson, but you'll see them a lot. We talk about functions as being f of x, right? If we say f and we put a little prime symbol, like a little apostrophe there, that is talking about a derivative. Okay. We also use the symbol dy over dx. And where that comes from, I'm going to just go off to the side here. I don't know if you need to write this down. But if you've taken science classes, you've probably seen this notation, the delta, the symbol delta. So that slope formula that we talked about up above, we could write it as change in y. That's what delta represents, is change over change in x. And this eventually over the years got adopted into this dy dx. That's what we're talking about, is derivatives are a slope. And I cannot emphasize this enough, that when we're finding derivatives, all we're really finding is a slope. But we're going to need some special mathematical tools to find that slope. By the way, sometimes we say our functions are f of x, and sometimes we just say they're y equals. So we can also write derivatives as a y prime, like that. Okay, so all of those mean we're taking a derivative of something. And like I said, that's going to be a really big topic as we go on. Okay, so let's look at an example here. It says a rock breaks loose from the top of a tall cliff. We're going to just sketch the following. So the rock's average speed over the first 2 seconds. So speed is talking about how quickly are things changing. This is distance, right? This is a height, and this is time. So I want to do height over time. That's essentially a slope, right? And so if I want to look at the change over the first 2 seconds, here's my position at 0 seconds. This is my position at 2 seconds. And so my average speed would be that secant line between those points. Because what that line is going to tell me is how quickly is my height changing per every unit of time, whatever my time is being measured in. Okay, so this is that first one, the one that I marked here in blue. Okay, this is an average rate of change, and I drew a secant line to represent that. But if I want the speed at exactly 2 seconds, that's where a tangent line is going to come in. So I'm not connecting 2 points now. I just want to focus on this 1 point here. And so in order to figure that out, what I would need is a tangent line. I would need a line that kind of brushes against the graph like this. And if I could find the slope of that purple line, that would tell me the speed at exactly 2 seconds. Okay? So see the difference between these questions. This is an average speed, and this is the speed at exactly 1 point. Okay. This local linearization, I don't know if you're ever going to hear me use that word again, but we do this with derivatives and tangent lines sometimes. We write equations for these tangent lines, and then if I were to zoom in really close on just that 1 point, I mean, it only touches the graph in 1 point, but when you're close to that point of tangency, that tangent line is really, really close to the function itself. So if for some reason we did not have an equation for the function, we could use that tangent line to do an approximation as long as we're close to that point of tangency. If we tried to go way up here, I mean, this tangent line is not going to line up with the actual function. But real close to that point of tangency, we can do some estimation with our tangent line. Okay, so today what our big focus is on is not even so much finding derivatives, but it's writing the equation for a tangent line. So this is the big deal today. So we want to write an equation for that purple line right there, okay? In order to write an equation, we need 2 pieces of information. We need a point and we need a slope. So we need point, so we need like an XY coordinate, and we need a slope, which usually we use M to represent a slope, okay? I don't know if you're familiar with this form of a linear equation or not. It's called point-slope form. You may have seen it in Algebra 1, you may not have, but we're used to talking about mx plus b when we talk about linear equations. The problem with mx plus b is you need a y-intercept, and the point that we're going to be talking about is not always a y-intercept, and we don't want to go through the trouble of finding that y-intercept. So this is another version of a linear equation that we're going to use. And so remember those 2 things we talked about here and here? There's your slope, and this right here and here are your point. Now if we simplified this thing, we could turn it into an mx plus b equation, but we don't need to simplify it. We are allowed to just leave our tangent lines written just like this, okay? So for today, this is going to be really easy because I'm going to hand you all of the information that we need. Okay, find an equation for the line tangent to this graph, x squared plus 3, at x equals 2. Okay, so this right here is part of my point, right? My point will be 2 comma something. I'm going to need to figure out what the y value is here in just a second. And then it says, given that f prime of 2. Okay, this f prime, that's a derivative. And remember what the definition of derivative is. Derivative is the slope of the tangent line. So this is me telling you what the slope is. I want you to enjoy this moment, okay, where I'm telling you what the slope is, because usually I'm going to make you find what the slope is, but I haven't taught you enough to make you do that yet. So right now I'm just going to tell you what the slope is. So the only real math we need to do here is figuring out this y coordinate. So I'm going to find f of 2. 2 squared is 4, and 4 plus 3 is 7. And so then my equation, I'm going to follow this form here. I'm going to say y minus my y value of 7 equals my slope of 4, and then x minus my x value of 2. And that's it. I'm going to leave my equation right there. That's good enough for a tangent line. I don't have my camera set up to be able to capture Desmos. Maybe I'll add a clip on the end and I'll come back to this example and prove to you that this gave me a tangent line. But that's my equation for my line that would be tangent to the graph, meaning it's going to touch this graph at exactly 1 point at x equals 2. And then it says use your tangent line, so that's this thing up here, to approximate the value of f of 2.2. Okay, so from my tangent line, I'm putting this in for x. So I'm going to say y minus 7 equals 4 times 2.2 minus 2. Okay, well this is just going to be 0.2 and then multiply that by 4, so I'm going to get 0.8. And then move the 7 over and I get y is equal to 7.8. So that right there is what this question was asking me to do. That is my answer to this question. I want to show you real quick, and I'm going to cheat and use a calculator here a little bit, but I want to show you what the actual value of 2.2 is when I plug it in. So when I do f of 2.2, I would do 2.2 squared plus 3. Let's see, I don't know if I have a calculator here. Oh, let's see. Okay, had to cheat a little bit, but this actually comes out to be 7.84. Okay, so that gives you an idea that, like, this is our approximation. This is what we were trying to approximate, but this would be the answer to our question, as we can say it's about 7.8. Okay, last one here. Example 4. Okay, so we've got a metal wire, and we're heating up the one end, and obviously metal will conduct heat, so the rest of the wire will start to heat up. Table below gives selected values of the temperature in Celsius of the wire from the heated end. Function is decreasing and differentiable. Those words probably don't mean too much to you right now. Those will be important in the long run. You'll probably see this same example pop up somewhere else, and I'll have more bullet points after it. This is to estimate t prime of 7. Okay, so here's the problem. First of all, I don't know what the function value is right at 7. I actually don't need to know. But what I'm asking is, what would the slope be at 7, right? How fast is this temperature changing at 7? I can't figure that out from the information in this table. Okay, this table is just individual points on the graph. It's not enough for me to come up with a slope. That's why this says to estimate. Okay, I'm going to estimate this by doing an average rate of change on either side of 7. So I'm going to do an average rate of change here and here. I need to emphasize again that this is an estimate of t prime. So we're not actually finding a derivative here. We're finding an average rate of change. Okay, but sometimes that's the best we can do. So let's see, 55 minus 62 over 8 minus 6. Let's see, this is going to be negative 7, I believe. Yep. Over 2, which is negative 3.5. Okay. So what this actually is telling us is that on average, when we go from 6 centimeters to 8 centimeters, the temperature is changing by 3.5 degrees. It's decreasing by 3.5 degrees for every centimeter that we walk along this wire. Okay, that's what that actually means. Because this is asking us for an estimate of t prime, we want to talk about it as though it's t prime. So we're not going to talk about it being an average rate of change, even though that is technically what it is. Okay, we want to talk about it by saying at, what did we use here? At x equals 7, the temperature it's changing. Specifically, it's decreasing because this is negative. Decreasing by 3.5 degrees. So I gave a label to that 3.5 per centimeter. Okay, so derivatives are rates of change. So we want to say, how is it changing and by how much is it changing? And so your label will always be a something per something. Specifically, it'll always be like this per this, right? So it's degrees Celsius per centimeter. okay, because that's what slope is measuring. So that's how we would answer this question. Okay, that's it. That we're really setting the stage here for some much bigger ideas, but for today, if you can write equations for tangent lines, if you can estimate derivatives off of tables and things like that, you should be okay. And we will continue with this really through the whole rest of this chapter and the whole rest of this year. So good luck. Let me know if you have questions when I see you again in class.